Looking at this split-screen diagram, we can observe the limitation of traditional coding assistance. On the left, a single cursor predicts the next few lines of syntax in isolation. On the right, an autonomous system analyzes and modifies an entire network of files simultaneously. Legacy models operate strictly within the file you currently have open. Because they lack awareness of your routing logic, your database schema, and your external dependencies, they generate code that often conflicts with the broader architecture. Claude Code integrates directly into your terminal to read your entire project structure. It locates the relevant files, proposes the necessary structural changes, and implements them across the local environment. Integrating a system with this level of agency changes the developer's primary workflow. Time spent manually typing syntax is reduced as the focus shifts toward managing high-level architecture and data flows. Because the system is interacting with the entire codebase at once, the reliability of the output depends on the structural integrity of the environment rather than just the wording of a single prompt. This necessitates a move toward rigorous system design over simple prompt engineering. The primary engineering challenge is bridging the gap between an isolated text generation model and a live, dynamic local environment. This schematic details the 5-layer stack. The context layer feeds project files into the reasoning layer for logical decisions. The tool layer grants external access, wrapped by an automation loop. Finally, the integration layer caps the entire structure, providing programmatic control over the agent. A coding agent is only as intelligent as the data it is fed. The exact quality of your output is determined by how well you control the flow of information between these 5 layers. You can deploy the most capable reasoning model currently available, but it will fail if it is starved of relevant context or overwhelmed by noise. Dumping an unorganized codebase into a context window floods the reasoning layer, degrading the model's logic. The solution is explicit context scoping. Strict filters strip away unused assets, isolating only key functions, dependencies, and documentation. A well-organized project naturally aids this process. Clear file structures and distinct entry points allow the AI to self-route efficiently, accurately pulling the exact files it needs to solve a problem. When you complete a feature and move to a new bug fix, you must immediately flush and refresh these context boundaries. Carrying leftover context from a previous task leads to degraded performance on the next one. Curating this signal-to-noise ratio is a foundational skill required to operate an AI coding workflow. Even with perfectly scoped context, the reasoning layer is trapped. Without external tools, it can only generate text suggestions. It cannot test a hypothesis or alter the environment. This diagram shows the Model Context Protocol, or MCP. This tool layer connects the reasoning node to your file system, version control, and APIs. The agent can now execute database queries or run browser automation without human routing. Integrating directly with GitHub allows the agent to pull down active issues, read the tracking history, and automate the initial pass of a pull request review. Because MCP is an open standard, you can view these servers as a universal plugin system. You can connect Claude Code to any data source or tool that supports the protocol. Equipping the reasoning model with this tool layer upgrades it from a passive advisor into an active participant capable of altering the project environment. At this stage, the developer remains a bottleneck. If you have to manually instruct the AI to run testing and linting after every code change, the workflow cannot scale. To eliminate this manual prompting, we rely on hooks. This is the core automation layer. This graphic maps a hook in action. When a specific condition is met, like saving a file, it triggers a chain reaction. For example, intercepting a Git commit to check dependencies. If an error is found, it's routed back for autocorrection. The architectural risk here is misconfiguration. Poorly defined trigger conditions will cause the hooks to overfire, slowing down your terminal and creating performance overhead. When calibrated correctly, hooks act as the automation backbone. They allow the system to continuously audit and self-correct against your engineering standards in the background. A functioning autonomous loop on a single machine is useful, but engineering teams require consistency across multiple developers. Teams achieve this by writing custom commands. These package complex prompting strategies and standardized refactoring operations into reusable terminal triggers that everyone shares. To integrate these capabilities fully, you utilize the Claude Code SDK, establishing direct programmatic control. Looking at this schematic, you can see how the SDK bypasses standard user interfaces. It allows you to extract the reasoning and tool routing capabilities of the agent and embed them directly into your proprietary internal developer tools. Mastering custom commands and the SDK takes a localized productivity tool and scales it into enterprise-grade infrastructure. To observe the value of this architecture, we can track how all 5 layers execute in a single cohesive lifecycle during an autonomous commit. Here is the fully assembled stack in motion. A task definition scopes the context layer, filtering noise. Refined data drops into the reasoning core, which uses MCP tools to execute changes. Finally, the automation layer hooks validate syntax and finalize the workflow. The most effective way to adopt this framework is incrementally. Start by executing tasks manually. Once you identify a repetitive operational pattern, encode it directly into an automated hook. The operational advantage of Claude Code is derived from the frictionless orchestration of this 5-layer loop. The legacy definition of a software engineer centers around the manual translation of logic into syntax. In an AI-assisted environment, syntax generation is handled by the model. The developer's daily priority shifts to managing context boundaries, writing clear instructional routing, and configuring tool integrations. In this live environment, we see what that orchestration yields: a system that analyzes, assembles, and optimizes complex architectures at speeds impossible for manual typing. The modern technical leader delegates localized coding to the agent. Their job is to design, deploy, and govern the structured systems that allow that agent to operate autonomously.